Hello, everybody. Welcome to the last morning of Real World Crypto 2019. I'm going to be popping up at different points during the day to say exactly the same thing. We're now planning for 2020. As you can appreciate, it's a very big conference to organize, and therefore we need sponsorship. I've already had 2 companies have already come up to me, new sponsors already during the program already this time, to add them to the huge list of sponsors. If you're a company and you don't already sponsor us, just come up to me, give me your email, and then give me your money, and we will make sure that you're put on the list of sponsors for next year. And with that, I hand over to the boss.
Oh. Thanks. Good morning, everyone. Good to see some of you here this morning, the morning after the night before. How many people had margaritas? I had 1, 2, well, maybe more than that. Anyway, let's get started. So we've got 3 talks in this session, and the first one is going to be given by Anders Erbsen from MIT, and it's about efficient and verified finite field operations. Thank you, Anders.
Good morning, Real World Crypto. Thanks to all of you who have come here at 9 a.m. braving blockchain and sleep debt. And I'm going to talk about work that me and my colleagues have done at MIT to produce high-quality implementations of finite field arithmetic for elliptic curves and other crypto systems with proofs of functional correctness and generally good implementation style. Now, here is an example of the state of practice today. It's for the P2F6 elliptic curve, the multiplication routine. And on the next slide, you can see the corresponding module reduction. And for most of you, the font is probably too small to make any sense of at this distance. And you're not missing much insight anyway, because all of this is really hand-unrolled, low-level optimized code based on a more general algorithm. But it's not just the low-level optimizations that make this kind of code tricky. Even if you look at the algorithm on its own, this is the 32-bit version of it, it is still not obvious that it does the right thing, or even that it corresponds to P2F6 at all. So in reality, what happens is that there are experts, many of whom are in this room, or at least were yesterday, who write this code meticulously for every combination of the desired operation, the prime modulus, and the hardware architecture being targeted. And these experts are really in demand. There is a lot of work to be done, and every person who specializes in this field that I've talked to has a backlog and a future log of implementations they wish that could be improved and that could be written in the future. So we decided to do something different. And by different, I really mean we built a different implementation. We implement the same interface as everybody else. Our code can be linked in place of existing implementations with relatively little effort. However, from the get-go, we insisted on machine-checkable correctness proofs. So we used the coq-proof assistant, and every operation, including the non-performance critical ones like serialization and deserialization, has a proof. And these proofs compose together to a proof of a full elliptic curve operation. Furthermore, we did something rather unconventional. We used the same source code for multiple primes and multiple hardware architectures. So we write one unsaturated Salinas reduction implementation that works for Poly 1305, Curve 2119, and Curve 448 if you are willing to forego Kurzüber multiplication. And it actually turns out it worked really well. When we first got the full pipeline working, the C code that it spit out after compile time specialization performed better than expert-written C code we had found on the internet by that date. And throughout this entire work, we have enjoyed a fruitful collaboration with the Titan and Boring SSL teams at Google. Both of them use our implementations for multiple NIST primes, or at least P2F6 in both of them, and Curve 219. Furthermore, some open source libraries like WireGuard and Ring in the Rust language link our code. And maybe there are others, but we haven't really done a census. So just to dive right into it, let's take a look at what the generated code looks like and what needs to be provided for every specific curve to get some code out for it. Let's try an implementation using the unsaturated Salinas strategy. Let's name it my curve. And let's pick the prime 2 to the 255, minus 19. And the minus, for some reason, did not fit in this command line interface, so it's not there. And let's synthesize multiplication that includes carry, and let's do it using 10 limbs on a 32-bit machine. So here it is. It is essentially modular variable names. It is roughly the same code an expert would write if given the same task. Furthermore, the same trick can be repeated with different parameters. So we're calling the same code generator binary. This time, the prime is 2 to the 130 minus 5 for a 32-bit machine. And again, here is the partial products of the multiplication. Here is the module reduction at the end. And on top of the generated implementation is also a comment that specifies bounds on the input and output limbs of this operation. These bounds are taken straight from the correctness proof of this code in Cog. And even if you are not proving the code that calls this function, these bounds are a sufficient description of what is going on here to use it safely. And for some primes, like P256, more complicated implementation strategies are necessary. So we have a different code generator for each implementation strategy. And this is the word-by-word Montgomery strategy as used in the fast assembly code in OpenSSL. Our code is not that fast, mostly because it's C, but it's still very good, and there are still proofs. And perhaps if C compilers were able to compile carry flag access better, it could be as fast, but that's not today. Now, let's go back and look at what is actually going on under the hood to make this happen. At the center of our strategy is the Cog proof assistant. So the Cog proof assistant is made for primarily mathematics, also program verification. And at the center of it is a functional programming language in which definitions and theorem statements can be written. So there are no built-in verification conditions. You need to write your own code and then write what you want to prove about it. And then it is actually totally up to you how you come up with a proof object that the Cog checker will check. And the checker is the same for all proofs. So we did not make any changes to it. You can download the vanilla version of Cog, and our proofs will check in it. And the proofs are usually generated through some rather ad hoc scripting or in a more principled manner using a proven correct static analysis pass or a compiler. And we rely heavily on these features that you can prove an algorithm correct and then use it in a proof. So first of all, we need to write the specification of what it means to have finite field arithmetic. This is really simple. The Cog standard library includes mathematical integers. So we define field multiplication as integer multiplication followed by integer module reduction. Each specification is one line for the operation itself, plus 1 or 2 lines for the bounds of inputs and outputs. Then, for each implementation strategy, so these are things like Salinas reduction or Montgomery reduction or variants of thereof, we write the generic template implementation. So this template here is a Salinas reduction one shown on the slide. Will work for multiple primes when passed different parameters. Of course, it is possible to pass it silly parameters, in which case it will be very, very slow. But it will still be correct. In fact, we prove that it is correct regardless of which parameters you pass to it. But executing this template directly would be slow because here, this one, for example, operates on linked lists of limbs. So that's not going to roll in the real world. We have a compiler pipeline that, given an implementation and specific parameters for it, will specialize it and compile away all uses of dynamic memory allocation or references to weights of limbs that are sometimes present in the template itself to produce C code just like the one we saw. And of course, in the end, we pass it to a C compiler. Depending on the C compiler, it is most likely not verified, but our own specialization pass and the micro-optimizations it applies and all the templates are verified in a manner that the proofs compose to make an end-to-end certificate of correctness of the generated code. Now, there are several important design choices we made in the writing of the templates that make them easy to prove correct and allow them to generate efficient code. And in the beginning, we actually started with much more complicated templates in hope that it would generate us better code and, that it should be hard work to write those implementations. But what I'm going to show in the next couple of slides are templates that are a couple of lines each and perform interesting arithmetic operations. However, to make this happen, there are a couple of conventions we have decided to follow. First of all, the templates work on mathematical integers, so there is no overflow. Of course, that means the compiler later needs to infer for each intermediate variable a fixed width in which it can be stored. Similarly, each field element is represented in the high-level implementation by a list of pairs. So normally you just have limbs, and the value of each limb is in the ith index. For us, each limb also carries its own weight. So if index 0 has weight 1, there is a pair 1, x in our representation. And that allows the high-level implementations to inspect the weights and branch on them, for example. But all those weights, if the implementation is actually reasonable and does represent fast code, are removed through constant propagation during compilation. So none of that remains at runtime. So here is the first implementation. And it's in a functional language, which I realize some of you may not be familiar with, but please bear with me. It takes as input, I hope I will get a pointer on here. Yeah. It takes as input 2 lists of pairs. So the first element in each pair is the weight, and the second is the runtime value, and produces another field element in the same representation. Then it iterates through both lists. So the map is the functional version of iteration that we apply here. And for each pair of input limbs, it produces one additional limb that is a partial product in that schoolbook multiplication sense. The weight of the new partial product is the product of the old weights, and the value of the new partial product is the product of the new values. And this works for any representation, including non-uniform radixes, for example, the one used for curve 219 and 32-bit architectures. And notice that this code here will just leave around multiple partial products with the same weight, or multiple partial products with slightly differing weights in cases of non-uniform radix. But these can be aggregated later in a separate function that during compilation gets composed with this one and results in the code you would expect. But writing it separately is useful because then we can write the proof of its correctness separately. And this proof, the complete proof of this multiplication is on the slide. It consists of 2 lemmas, one for each loop. So the inner loop multiplies a list by a single limb, and the outer loop multiplies by each limb in the other input. And most of the proof is delegated to the algebraic reasoning tactic NSATS that uses Krömer basis computation and is a part of the Coq standard library. But schoolbook multiplication wasn't that tricky to begin with, so perhaps it's not an instructive example. Let's look at something harder. Here is a general implementation of module reduction that is sensitive to the shape of the prime. So it is a generalization of the P256 code that I showed earlier and the standard techniques used for curve 209, curve 448, poly 1305, and so on. In the code here, we have made an important convention to represent the modules as a difference. For S, the first part in the subtraction is the power of 2 that is just greater than the prime. And C is the difference between the power of 2 and the actual value of the prime. And then the first lemma, we proved that, yep, you can reduce modulo the prime by just replacing the coefficient of the high half. So S is the power of 2, and B is the high half of the thing you're reducing. And you just replace S with C, and you have the same value modulo the prime. Notice that this first lemma does not say anything about limbed representations. It's just if you have anything that is A plus power of 2 times B, you can reduce it this way. And then the definition in the middle of the slide, called reduce, takes in the prime, again, in the representation, where the power of 2 is known separately, and the difference between the following power of 2 and the prime itself is represented as a limbed difference. So for curve 209, that is 1,19. For P256, that is each of the taps in a separate limb. And then the actual input that is being produced, here it's called P, is split into the high half and the low half. The split function inspects the weights of each limb and the input. So weights that are bigger than 2 to the 155, or technically divisible by it, go into the high half, and the small weights go into the low half. And then the module multiplication trick proven correct in the first lemma is applied directly. Of course, we call limb-wise multiplication and limb-wise addition to generate the expected multi-limb reduction as, for example, seen for P256. Now, if you take this code and plug in S and C to make P256, you will actually generate the reduction algorithm shown in the NIST documentation that I had on slide number 4. But perhaps more important than that for expediency of this implementation strategy is that the proof, or this entire reduction algorithm, is again on the slide. This time it is a long line. I had to stretch the text box a little bit. But it is still completely tractable, and you only need to do this once when writing this implementation. Now, of course, that it actually specializes correctly. It wasn't even obvious to us before we wrote this code. But in hindsight, everything is 2020, so let's take a look at what the specialization phase actually has to do. And OK, so there is a slide that says we have more implementations of other strategies that I forgot about. There's definitely saturated Salinas reduction that handles carries between different limbs, and there is also a variant of Bure reduction that was used in Google Titan. So what does the compiler do to turn this high-level functional code into C code as you would expect to find in a crypto library? First of all, as I showed in the live demo, the lists of limbs have known length. So we asked for a 10-limb implementation or a 5-limb implementation. So it just expands the list and creates new variables for its elements. Then the loops that iterate over this list can be unrolled, and this generates more intermediate variables, say 1 for each partial product. And of course, once we have those variables, we can optimize the definition of each one separately, applying arithmetic optimizations such as replacing multiplications by powers of 2 with bit shifts and modulo with binary masking. At this time, these are all still mathematical integers. No overflow is accounted for. And in the proofs, we have assumed that overflow does not happen. However, the inputs are assumed to be within some range. So in the code generator, we actually use a heuristic to pick a starting value and then trace the bounds of each intermediate variable through the code and check that the final outputs are within the smaller bounds than the input was assumed to be, so it can be called on its own output. And this proceeds step by step, and based on the inferred ranges, fixed width integers are assigned to each intermediate variable. This is the only step that is not standard partial evaluation. So everything else you could just think of, oh, it is constant propagation. But this one actually changes from mathematical integers to fixed size integers. And the output bounds are also included as a part of the documentation in case a developer wants to use these field operations directly in a non-proven environment. And when we first started doing this, we used Coq's built-in call by value evaluation strategy with a blacklist of which operations not to unfold to perform partial evaluation. And honestly, it was really convenient. You just write the list of things you don't want to unfold, and it does it for you. But it also had surprising asymptotic complexity in that when we first got P256 working, next morning I tried to synthesize P384 code, and I waited a couple of hours, and it still wasn't done. But then Jason went and implemented a verified partial evaluator inside Coq. So it is a functional program that takes in another program and produces a third program. And it's proven correct in the sense that all input programs are mapped to equivalent output programs. And this proof links with the field operations proofs for the high-level language. So the top-level theorem we were proving did not change, even though we switched to a totally different specialization strategy. So, I would say Coq is both the biggest downside and biggest upside of Coq. That you can do this, but you need to do this sometimes. So enough complaining about performance. Let's say some good things about performance. The compilation is really slow, but the compiled code is really quite fast. For Curve 219, the code that we produce is roughly on par with the fastest C code we know. It depends exactly on which microarchitecture you benchmark it. On my laptop is always faster, but other people tell me that they have something else be faster. And for P256, it is the fastest C code, but assembly code is significantly ahead. This is because of the carry flag optimizations I mentioned earlier. And we also scraped curves at moderncrypto.org for prime numbers and benchmarked all of them. And for most of them, we couldn't find expert implementations because nobody had put in the effort to write them. But we're at least much faster than GMP, so that's good. GMP is the GNU multi-precision library. But of course, we had to integrate this code into a real library, and the code reviewers smirked at us and looked at us another time. And in the end, the pain points ended up being that nobody wants to depend on Coq to build their crypto library, so we had to check in generated code. Generated code has gibberish variable names, x1, x2, and so on. It also has no comments and no suggestive whitespace. But in the end, our code was judged against the quality of the code that it was replacing, which also had no comments and no suggestive whitespace and gibberish variable names. So it was generally seen as an improvement, perhaps because of the little difference that we have high-level specifications that are proven to be equivalent to the code. So are relatively justified in just skipping reading the code altogether. And then we actually, well, when I was working as an intern at Google Boring SSL, went and refactored all the colors of the Crypto9 library to use different types for field elements that are in different bounds. And this also turned out relatively well, because then I could just document that the definition of the dummy struct of what bounds are assumed to be known of its limbs. And in some cases, we even went the other way around and prescribed the outer finite field implementation into Coq to prove it correct as an entire unit instead of verifying individual field operations. But of course, this could continue that infinitum, and perhaps I want to do something else for the next couple of years. So here are some things I would like to see happen, but I'm probably not going to work on. First of all, the performance issues we hit on Coq, we believe, are almost entirely spurious. There is no fundamental reason Coq would have to be slow. It is simply software written by mathematicians, and it does very good mathematics, so we should be happy for that. Similarly, the open source C compilers could do much better on allocating carry flags. ICC is slightly better already. That would be a great improvement, and we could, of course, prove more stuff. But all of this is not really exciting in an academic context, and perhaps if the real world wants it, the real world should find the resources to actually get it done. I'm happy to hear questions.
So it's probably never a good idea to admit that academia is not the real world, but we have time for questions or comments. Just come to the mics. Watson, you want to ask a question?
So I have a question about the reliance on Grosvenor basis algorithms. Is there a certificate generated in Coq that the ideal membership is in fact correct, or are you relying entirely on the correctness of the Grosvenor basis algorithm?
This is the standard Coq proof checker. There is no reliance on the correctness of the algorithm. The way it actually works is that the Grosvenor basis algorithm produces polynomials by which to multiply the givens to produce the power of the goal, and thus certify that it is 0.
Hello. You mentioned about comparison against GMP. Have you done a similar comparison against BN, OpenSL's big number? And how does it?
We did not.
Okay. Thank you.
Hi, thanks for your talk. Do you have any idea of the man hours that you spend in verifying that, and how many lines of code do you have?
Oh, it was a lot of man hours, but a lot of it went into figuring out how to structure this entire project. And in the end, the high-level algorithms are really as simple as I showed on these slides. The compiler is rather complicated. It has, I think, more than 10,000 lines of code now, in addition to standard library extensions that MIT maintains for all of its projects, all of its Coq projects. So there is quite a bit of fixed cost to build the infrastructure, and Coq itself is a many decades in making project. But adding a new implementation strategy is very easy, and using an implementation strategy for a new prime is really easy, as I just showed in the demo. So that's the cost model.
OK, thank you.
Yeah, thanks for the talk. This is really cool. I'm curious, so when you're writing handwritten code for crypto operations in C, you pay a lot of attention to, say, timing issues. I'm curious, did you sort of inspect the generated code to check for these, or how did you think about things like timing attacks and cache attacks?
So the low-level target language that is used for our code only includes operations that are believed to be implemented in constant time on common processors. So for example, there is no division in that language.
OK. Let's thank the speaker again, and we'll move on with the next talk. Thank you very much.
Mystery. Yes, there we go.
Okay, great. So next up, we have a talk entitled Verified Vectorized Cryptography, and the talk will be given by Karthik Bhargavan. Thank you, Karthik.
Thanks, Kenny. All right, so this is work with a bunch of people, as you can see there, but it's also part of a larger project which involves INRIA, Microsoft Research, CMU. It's called Project Expedition. I encourage you to check it out. So like the previous talk, the focus here is how do we build high assurance crypto software. Like we all know, writing crypto code is hard. If you go look at the vulnerabilities page of OpenSSL, just this year you will find multiple buffer overflows, you will find many side channel attacks. Occasionally you will find arithmetic bugs and field arithmetic bugs like the ones we saw there. So this is a problem, and not only that, all of these have a commonality, which is that these are kind of low probability bugs. As in, they're not going to be found by testing, but if you know they exist, they might be possible to exploit. So like Andrew said, we also kind of promote the idea of using formal verification as a principled approach to systematically eliminate large classes of bugs. And there are many tools, and we use a tool called F-star to do this. But verification, in my experience, for these kinds of things often is a significant effort. So, like the question was just asked, it can be a PhD burning effect is what I call it. You can take a PhD student, send them off for 2 years, and they'll come back with either an amazing tool for finite field arithmetic or a proof for a few primitives. And that's great if you only want to verify this library once and for all. And for a lot of things, maybe you never want to change the code. Unfortunately, modern libraries are not like this. We have large full-scale libraries with multiple primitives, with multiple implementations in assembly for each primitive and so on. And so we want to figure out on how we can scale up these kind of techniques that we are talking about to work for real-world, large, modern libraries. Hint, we don't want these libraries to be so large. Okay, so that'll help us. But let's kind of set up the problem a little bit. If you wanted to write verified crypto code, what do you end up doing? So of course, you start from the RFC. So this is the Cha-Cha-20 Poly 1305 RFC, which has been extensively implemented over the last 3 years. But of course, you can't just start from there. You have to extract some pseudocode. And if you're lucky, the RFC actually has pseudocode in it in a Python-like syntax or something. So you don't have to make that effort. For some NIST RFCs, you have to make a big effort to actually even extract the pseudocode. So once you have that, okay, a programmer who can look at the pseudocode and write code in their favorite language, probably C in this case, and then they add some details, like how do you alloc memory, where do you free the memory, maybe you have a special kind of API, like an incremental API you want to present, which was not there in the original RFC, and so on. So there's some bit more work there. But in the end, for Cha-Cha-20, you can write the whole implementation in a couple of hundred lines of code. Of course, you might think, well, this is so small, it's obviously correct, right? But there are still some issues. You've started using memory, so you might want to make sure that your code is memory safe. You might have some timing leaks, like was asked before, so you might want to make sure, for example, any naive implementation of AES will have a timing leak. Is that the case here as well? You might want to ask these kinds of questions. Poly 1305 is slightly different, and as we saw before, the main thing there is, although it's a beautiful mathematical spec, polynomial evaluation over field elements, what it relies on in the heart of it is finite field arithmetic. And so when you try to implement this, the code is actually significantly larger. So if you wrote it by hand, it would be about 500 lines where each number is broken into 5 U32s and so on. And it gets a bit more complex, and you're worried about carry propagation bugs and these kinds of things as well. So that's the setting in which we are. And so if you wanted to verify the kind of code that we are writing here, which is C code and so on, the first step you'll have to do is you have to write a formal spec. So the pseudocode is still not enough. You still have to write that formal spec. Perhaps in Coq, perhaps in F-star, perhaps in Cryptol, but somebody has to do this, okay? And once you have that, then we can put the might of our verification tools behind it and prove that the C code you have at the bottom matches the formal spec. Now note that really in an ideal world, you don't just want to verify one small component of it, like just a field arithmetic or something. You want to actually extend it all the way up to the full primitive, because you don't want bugs in the polynomial evaluation or in the CTR mode or anywhere else. And you want to verify for side channel resistance. Well, it's whatever, constant time coding, so to speak, timing side channel resistance, as well as memory safety and functional correctness. And there's a bunch of tools that will do this for you. Our methodology for doing this is F-star, and we have built a library called Hacklestar, which we talked about last year here at Real World Crypto. It implements a bunch of primitives and verifies every single aspect of them for all the properties we mentioned here. You can go check it out on that URL. So once you have verified this code, you can compile it to a portable C code, standalone code, whose performance is comparable to and often better than handwritten C code. So there's no reason to write handwritten C code anymore. With fiat crypto, like we saw in the previous talk, and with this one, you can actually write code which is fast and also verified. And this one is used in Mozilla Firefox and other such things. But let's try to understand how much effort was involved. Okay, let's go straight to the effort question. So in the Cha-Cha-20 code and the Poly 1305 code for Hacklestar, just looking at those ones, the high-level spec was like less than 100 lines. Okay, it's very, very, very simple and nice. But the verified code we write is actually significantly larger. For Cha-Cha-20 and symmetric primitives like this, typically if you have to produce, if you want to verify, let's say, a 300-line C program, you will end up writing maybe 400, 500 lines of annotations for the memory safety, for functional correctness, and so on. And not all of it is interesting. Most of it is probably boring. For Poly 1305, you're also doing field arithmetic proofs, so you might be writing 7 times as many proof annotations. So it's still significant, but if you only wanted to verify the reference implementation of these algorithms once and for all, maybe this is a worthy effort, and you can do this. And of course, as we learn more and more about these tools, we can use tools like the one presented in the previous talk to make this effort less and less, right? The problem is verifying that C implementation isn't enough, because in fact, even though we delivered our beautiful C code to Firefox, that code is actually never used in practice, because every single library has a bunch of other assembly implementations optimized for each different platform, and those are the ones that are going to be selected at runtime, not the nice reference C implementation that we verified. And for good reason. On a modern laptop like the ones you have, it's probably going to get a 4x improvement, 4 times improvement in speed between the C code and the assembly code for certain primitives, not for curve to 5509. That is one where actually you don't get so much improvement, but for Poly and Cha-Cha, definitely. So why would anybody use that C code? So if you go look at the OpenSSL code, in fact, there's like 8, 9, 10 assembly implementations of each primitive, and each of them is 1,000 lines or more. Okay, so now we were in a nice world where you had to verify 500 lines, and now we're in a world where you have to verify 10,000 lines. Let me just tell you, this isn't happening. Okay, so this is not happening. So it's probably also awful for the people who have to maintain this stuff, because the more code you have, more things can go wrong, more fiddly bits. I don't know how they do it, but there is way too much code. Even in boring SSL, there will be 5 implementations of Cha-Cha-20 in assembly, and I think at least 4 for Poly 1305 as well. And the main reason they're there is because of vectorization. Each of these ones is doing specialized vectorization for ARM, Neon, for AVX, AVX2, SSE3, and whatnot. So this is a hard target for verification. How do we scale up our verification to deal with all of them? I don't want to verify each of them individually. So the key idea that we are promoting in this talk is that we don't want you to write individual, separate, completely independent implementations for each platform. We want to rather identify the parallel algorithm you're trying to implement and the optimizations therein, and write a generic SIMD implementation that we can verify, and from which we can compile down to individual SIMD implementations for each pattern. Okay, so in this way, maybe the performance might be slightly less, but at least you get a baseline performance from which you can optimize. As I will show you, the performance you get is actually pretty good. So the architecture we're going to follow in this talk is the following. So it's a bit of a hairy picture, so I'm going to introduce it step by step. We start off from a spec for the crypto algorithm we're going to do. And this is going to be written in a domain-specific language called hackspec that I'll describe in a minute. From that, we're going to compile down to a formal specification in F***. Then we're going to write a vectorized algorithm, a completely generic vectorized algorithm that doesn't care about how big your vectors are, what specific platform you're on, but it's basically a parallel algorithm that implements the same primitive. And we'll prove that this is doing the same operation as the high-level spec. Okay? So this is a pure spec-to-spec transformation. Then we will write a stateful vectorized implementation of this, and all of this are going to be written in a language called F***. And we're going to prove that the implementation matches the vectorized algorithm. And in addition, of course, that the implementation doesn't have memory safety bugs or side channel problems and so on. So we'll do a bunch of verification on the implementation level. But those things on the right have been mostly automated over time, and we've kind of got a very good understanding of how to do this almost without any new annotations. And once you've verified everything, we can just compile it down, and this one special case of the vectorized code is going to be the scalar code, which can be used on any machine. And then there are going to be, if you want, you can generate code for 128-bit, for 256-bit, 512-bit one from the same source code with no difference, okay? Because it's been verified once and for all these widths. So let's see how this goes through for one example, okay? Okay, and before I do that, the whole point of this architecture is that at the end of it, you get really optimized code on the bottom right, which has been proved correct with respect to this very simple spec on the top left, okay? Most of the steps here have been automated, except for the big part here, which is on the bottom left, which is the proof that the vectorized algorithm, the generic vectorized algorithm meets the high-level spec, and that's where most of your manual effort is going to be. But this is good, because this is the interesting part of the proof, and this is where we want to spend our manual effort, if any. We don't want to be spending it on the other stuff, which is kind of boring, okay? So all of this is built around a language called F-star, which is a verification-oriented programming language. If you write code in F-star, and if you know OCaml or F#, it kind of looks like that. If you're doing proofs in F-star, it kind of looks like Coq, except that you have access to a SMT solver called Z3, so a lot of the simple kind of proof obligations you might have are automatically discharged. And once you've done your proof in F-star, you can compile it down to OCaml, to C, to WebAssembly, whatever you like, okay? So you can try out the language. It's a pretty cool language. It's developed at Microsoft Research mainly, but also with collaborations with INRIA. So let's go to the first step. We're going to write the spec that we're going to verify against. So the first point I would like to make here already is that we, as verification people, should not be writing the specs, right? We are trying to prove something, but why are we writing the specs? Somebody else should be writing the specs for us. In fact, the people who should be writing the specs are the people who are writing the standards, or even better, the cryptographers who actually designed this thing. Instead, we are trying to figure out what the spec is by reading these really obscure textual descriptions that come out and trying to extract it ourselves, which is a wasted effort, and there could be a gap between what the RFC says and what we are doing. So instead, we have designed this to kind of make it easier for cryptographers and standard authors to write formal specs. We designed this DSL called HackSpec, where we've written a whole bunch of specs already. It looks kind of like the pseudocode you will see in standards. In fact, it is a typed subset of Python 3, and I'll show you an example in a second. You can write a spec in there, and then we have compilers that will spit out specs in other languages. So right now it works for a couple of formal languages, but we intend to spit out specs in almost all the languages that people are using. So this, we hope, will reduce the gap between what the cryptographers thinks we are proving and what we are actually proving, and also maybe will allow us to compare and compose the proofs done in different systems. All right, so this is what a hack spec of CHA-20 looks like. It's just the very first function in the spec, okay? It's the line function. So this is actually Python 3 syntax. This code runs in Python 3, but if you're a Python programmer, the thing that might look weird to you is all those type annotations, but they're allowed in Python 3 syntax. So here, this is a type subset. Every variable has to be annotated with a type, and the types that we have here include range types. So I can say that the index has to be between 0 and 15, the rotation value has to be between 1 and 31, and the array has to have a length which is exactly 16, and so on. So these are sort of kind of fairly detailed types that we are giving these. And then we write the specification. The specification consists of a series of functions, and each of these functions is observationally pure, which means that internally it can modify local variables, but it cannot have any side effects which are externally visible. And this is important to be able to compile them to many languages like Coq and Star and so on. But once you return this code, you can actually run this. This is a spec, but it's executable. You can run this. You can see it pass all the test vectors. And when you're running it, it'll actually trigger runtime type checks as well to make sure that you didn't make some silly mistake when writing this spec. So this is a tool for writing a formal spec for a crypto algorithm. But once you've written that, we can compile it to an F-star spec, which looks very similar, but it's a different syntax. But it doesn't matter, right? You don't care. You're not even going to look at this as long as you trust that my F-star compiler, my HackStack X-star compiler is good. And F-star will do additional checks on this. It'll check all the ranges. It'll make sure that all the functions are terminating, and so on. Okay, but that's some additional sort of sanity checks on the spec. So we have the spec now. The next step is to write the vectorized code, right? But first we have to design our vectorized algorithm. So what are the vectorization strategies for CHA-20? There are typically two. One is what I call the line-based parallelism. If you look at the operations that are happening, that the function line that I showed you in the previous slide, you see all the places it's called. You can actually identify, if you unroll them, that 4 of them can happen at the same time. So you can do 4 lines, and then 4 lines, and then 4 lines, and then 4 lines. And so if you have a vectorized architecture where you can have 128-bit vectors, so you can operate on 4 32-bit numbers at the same time, you can actually make this go much faster. Okay, so that's one strategy. The other one is to say, well, forget about CHA-20. It's essentially a CTR spec, CTR algorithm, it uses counter mode, and so counter mode is inherently parallel. You can process any number of blocks at the same time, and that's true. And that's another way of parallelizing it. You just take different blocks and run them in parallel. We've done both, but I'm going to focus on the second because it's actually a bit faster, and it's actually a bit more generic. So this is what the first step of writing a generic CHA-20 vectorized algorithm is to take the static spec and you generalize it to work on any number of lanes, okay? So I've defined a type called lanes there, which says how many UN32s can I operate in at the same time. And I've just put some limits to it. I say it can be 1, 4, 8, I can add 16, 32 if you like, because those are the common vectorization patterns we have. But really, we don't care how many lanes there are. It's just that those ones we know how to implement efficiently. Then we define a type called UN32xn, which means it is a UN32 vector of size W. And our state basically becomes a sequence of these vectors. But if you think about it, the state is now internally representing W copies of the scalar state. So there are W independent scalar states that are included in one vectorized state. The code for line looks almost exactly the same, except that it is parametrized by the number of lanes W as the first parameter. And every operation that we are doing there is now a SIMD operation and not a UN32 operation. So it just means please do the same operation on every lane. Okay, so this is one of the simpler cases where the line function in the vectorized sense is simply a mapping of the scalar line function, but on all lanes. Just do the same operation on all lanes. But a surprising number of functions actually have this. So rather than writing the scalar code, I'm saying that we will rather write this algorithm, which is actually more general. Okay, so that's your vectorized spec for one function, but of course that's not enough. You've got to do that kind of vectorized implementation for each of the functions in the CHA spec, okay, depending on the SIMD library that we have. Then you have to do a little bit more work to define all the translations from the scalar state to the vectorized state and back. And these effectively are matrix transpositions, but for which we have a nice library to do these transpositions. And finally, you have to modify the overall counter mode encryption block to make sure you can process multiple blocks at a time. But that's reasonably straightforward, but that's the last thing, and then you're done. So now you have your vectorized algorithm. Is it correct? To prove it's correct, there's at least two steps. First, which is the easy one, I would say, for each function that we define, like the line function, you prove that the vectorized version is simply a map of the scalar one. So this lemma here basically says that if you run the vectorized line function and then you transpose the state, it is the same result as if you transpose the state first and then you ran the scalar line function on each component of the result. So it's basically, that's the correctness guarantee for this one. And then composing all of these, you can go all the way up to the top level encryption function and prove your main theorem, which is that the vectorized encrypt function has the exact same result as the scalar encrypt function. You don't care, it's just faster, but it's the same result. Okay? But note that all of these functions and all of these lemmas are parametrized by W. We don't care what your width is. It's still going to prove it for all widths. Okay? Well, not all widths, all the widths that we put in the lanes up there. All right, so we have the algorithm, we want to go to code. Okay? What's the difference? We already have the algorithm, what's the difference? Well, this is what the F-star code or stateful code for that particular function looks like. It's actually in a subset of F-star called low star that we can compile to see. The real code is just the bottom 3 lines of the slide. Okay, so it's not much. The rest of it is the preconditions and postconditions that you need in order to use this code safely. Okay? So the first thing is the memory safety precondition. That's the only precondition. It says that the caller of this function had better make sure that the st pointer is actually live in the current heap. Otherwise, you're not allowed to call this function with a null pointer, for example. Okay? The memory safety postcondition, the first postcondition, says I promise that I will keep all live variables live, as in I'm not going to deallocate or free anything, and I only modify the st variable and nothing else. And this is important if you want to call this function and other functions and compose the proofs. And the last postcondition basically is a functional correctness guarantee, which says I guarantee that the output of this function is going to be exactly the same as what the spec says it should be. Okay, the spec says the result is a line. I'm producing exactly the same result, except I'm putting it in an array and you have to look it up and stuff. And the code obviously looks very similar to the spec. In this case, is the simplest function you can imagine, but there are more complex functions where it might look quite different. And F-star will almost automatically prove that this function meets its spec. I mean, for this function, it will prove it automatically. For some other functions, you might have to help it a little bit, but not much. All right, so now we've gotten to code, okay? So let's compile it. We've done the whole step from hackspec down to vectorized code, and now we can compile it and spit out C. If you set W equals 1 and run the F star to C compiler, it's going to specialize the code, throw away all the dead code, throw away all the cases that are not relevant, inline everything that needs to be inline, and spit out C code, which is the scalar portable C code that will work on any 32-bit platform. If you set W to be 4, it'll spit out 128-bit vectorized code by linking to an intrinsics library, which then this code can run on ARM Neon or an AVX or SSE3 machine without any problem. So it's sort of, it's just producing 128-bit vectorized code. If at WA equals 8, 256, so on. You can just crank out as many implementations of this as you want, okay? As long as you have the intrinsics to actually implement the vectorized operations, it will just spit it out. So we've done all this work. This was the whole path we took, and we finally got to the bottom right. Of course, we did this just for Cha-Cha-20. We do the same for Poly 1305, SHA-2, SHA-3, and these kinds of things, whichever benefits most from vectorization. And the proofs will be slightly different. So when you vectorize Poly 1305, it's sort of, most of your effort is actually in proving that the vectorized field arithmetic is correct, and then you have to prove that the inherent parallelism that you're exploiting, which is the polynomial evaluation, has a Horner's rule, and you expand it out and so on. So the logic is slightly different, but the process is more or less the same. So what did we win? We did all this effort, what did we win? Well, what we get is we spit out 3 different implementations for Cha-Cha and 3 different implementations from Poly from the same implementation. The scalar 32-bit code that we get out from here is as fast as handwritten C code, so that's not a problem that you can see from anywhere. The 128-bit code is significantly faster. The 256-bit code is significantly faster. And if you go to the bottom and you see, well, what is the fastest assembly implementation of these things on your laptops, you'll find that, well, we're a little bit slower than the fastest assembly implementation, but not so much. And we came from a completely generic, non-platform specific code, okay? And we're coming down to that speed level. Of course, the precise numbers here, please don't pay attention. If you change the compiler, you change the operating system, small changes will change the numbers, but the rough shape of the numbers will stay the same. And what about the effort? Well, what was the effort to actually do this? All right, so we are hoping that the high-level spec, which is the hack spec, is going to be written by the cryptographers. That's not our effort, right? The green bits is what we have to write. So for Cha-Cha, we had to write about 1,700 lines of code plus spec plus proof, and for Poly, about 4,000 lines, okay? So if you look at it, and if you look at the C code that is actually generated, because they're generating 3 implementations of each, now our proof effort is far less than what the C code is, okay? But that's maybe not fair. And the way I would see it is, the amount of effort required to verify one scalar implementation of these primitives, that's the effort you still have to do, but you get for free all the vectorized implementations. Of course, we are generalizing this now and trying to do it for all the primitives in the Hackle-Star library, and as soon as it's done, we'll do a new release and so on. If you want access to the code we've already got, please ask me and I will figure out how to get it to you. We are already trying to deploy it in all of these places. Of course, just verifying the crypto itself is not so interesting. You want to lift it up and try to verify larger crypto applications, protocols, and stacks. And already we are seeing that the vectorized version of SHA-3 can be very easily used in many post-quantum primitives that we are also trying to verify and so on. And more generally, we are sort of working on 2 different projects, which you might have heard of, which are basically where the crypto library is just a crucial but one component of building a large verified security stack for the web, including Project Everest, which is where a lot of the developments that we are doing are coming from. I'm going to conclude with this slide where my concluding thoughts basically are that, well, we're all trying to build this high assurance crypto library and we want to apply this to full libraries, right? But to do that, this has to be a collaborative effort. Now, the kinds of the talk that you saw just before and this one, you've seen the limits of what formal verification researchers can actually give you, but we need help. I mean, we can't just do it, we verify all your code by ourselves. If you're going to dump 100 variations of assembly code, I mean, it's not really, we're not going to be able to verify it. Instead, maybe we can all help each other. If you're a cryptographer, maybe you can write formal specs so that we don't have to, and we can be sure that we are proving the right thing. And you can try Hackspec or you can try any of these other formal languages. If you're a crypto developer, try to rethink the way you're developing your library. Maybe there is value in defining generic algorithmic optimizations first, rather than always focusing on the low-level assembly language instructions that you are trying to optimize for. Well, that's it, and I'm completely out of time, so thank you for your patience.
Thanks. I think we'll make a little bit of time for questions because I see interest from the audience. So let's take a few questions and then we'll get the next speaker set up.
Thank you for your talk. I noticed that you were measuring effort in number of lines of code. How would you translate that to number of hours spent?
This is a fair question. And I think what happens is there's always a difference between the first time you do something and the second time. And this is actually the second time. The first time you do something, I think it's number of lines doesn't make any sense because it's probably you've done 25 versions of that thing until you got the right one. But what we've been really engineering over the last year and a half is to kind of identify all the patterns that we used for developing the first version of HackleStar, distilling them into libraries so that we have all that sort of domain knowledge, so that now I'm only counting the incremental effort done for every new thing. So that is getting pretty close to the line count. Okay, but yeah.
Thank you.
Thank you very much for the very nice talk. So in your overview of what happens from the top left to the bottom right, there were two steps that are labeled compile. So one from hackspec to fstar and one at the end from low star to C and intrinsics. Do I understand correctly that this compilation steps, the actual compilers, are not verified, right?
That is correct. So we for the big one, which is on the bottom right, going from F* to C, we have paper proofs that our compilation strategy is correct, but the software is certainly not verified, and neither is the C compiler we're using below. But yeah, indeed there is a trusted computing base here, which is not insignificant.
Okay, thank you.
Last question, perhaps.
So that was a very cool talk. So this question, maybe it's a bit unfair to just ask you and not the previous speakers, but if one were to begin a new formal verification effort of a different set of crypto algorithms that you all have implemented, and you can assume for the answer that I'm a person who's familiar with Coq, familiar with F***, what in your view, after having undergone this effort, are the trade-offs between using these two approaches? Which would you pick, I guess? Or what are the justifications for picking F* or picking Coq, I guess?
Yeah, it's certainly unfair to just ask me, but well, I would frame that slightly differently because tools are tools and everybody gets familiar with certain tools and they use one over the other, okay? But a bigger thing there is between synthesis and verification, okay? So when do we use a high-level kind of minimized spec and generate correct by default code? And when should we use code that somebody has written and try to verify that it's correct? And there are many projects that are trying to do both. There's a lovely project called Whale where they're actually verifying the assembly in OpenSSL right now. And I think there is room for both. So as you saw in my picture, there are some places where we compile, some places where we verify. We find that by compilation we can get pretty close, and Fiat certainly gets very close and better than handwritten code. But in some cases you do want to do some very specific optimizations that only work for curve 25519 but not for curve 448, And there are such optimizations that will just kind of lift you beyond. And people need this for certain primitives and they don't care for others. And there you do want to kind of come back and do some verification. And so it depends, I guess. My feeling from my talk and the talk before is that when you can, if you can synthesize from a small code base to the real one that you want to use, that's clearly the best one. But I don't think that's always going to be the case. So I'm pretty confident that people will want to write their own code and want us to verify it. So we have to find a middle ground between them.
Okay, thank you. Let's thank the speaker again. And we'll just get the third talk set up. Okay, so the third talk in the session is going to be given by Srini Devadas from MIT, and he's talking about towards an open Oh, I've just lost the title. There we go. An open source, formally verified, secure processor. Thank you very much.
Thanks, Kenny. Good morning, everyone. Thrilled to be here. As you can see, there's a lot of adjectives on my title, so I'll try and explain them as I go along. I want to point out the aspirational aspect of the first word there. So we're not quite where we want to go or where we want to be, but we're working towards it, and I'll talk to you about the work we've done really over the last couple of years trying to get to secure processors. And so if you look at what time-shared systems should give us, one of the things that they should give us is architectural isolation. We want compartments that are associated with processes, and we want privacy and integrity guarantees associated with these processes. And obviously that's fundamental to maintaining process correctness, as well as obviously the privacy considerations. But unfortunately, what's happened over the past few years is we have this picture here, which is there's all these leaks associated with information that are associated with breaking process abstractions. These process abstractions are broken for a variety of reasons. I mean, they may be broken because of bugs or features, but they are also broken because of side channel attacks. And in particular, what's changed in computer architecture really over the past couple of years is that people have realized that microarchitectural optimizations that are useful for performance and energy have these unintended really side effects that are associated with leaking information across processes, and things are exacerbated in the domain of secure enclaves, which is really going to be the primary focus of this talk, where you actually don't trust the software, you don't trust system software, and so now you have this malicious adversary who really has a lot of privilege and a lot of power over the individual processes. And so this notion, of course, of containers and enclaves predates microarchitectural side channels, but I think together they've sort of caused wreaked havoc on architectural optimizations. And so I'll hopefully give you a sense of that by the time we're done here. So I want to give you a sense of the attacks that we're considering in our work. And this is really a template for attacks. There's many specific attacks that fall into this. Obviously, attacks are combinations of in many cases, bugs, as well as these microarchitectural side channels. But if you kind of look into what's going on with Spectre and Meltdown and the cache timing attacks that really predated Spectre and Meltdown, you have essentially the picture here, which is you have domains. You have containers, domains, processes, what have you, and there's a victim domain and there's an attacker domain, obviously these domains should stay separate. And what happens is that you have a channel that's built potentially by the attacker, but essentially exists in the design in some fashion, which is this side channel. And it could be completion time of a process because the operating system can view the completion time of a process. It could be because of shared microarchitectural state, because you share a cache. It could be bandwidth, it could be an arbiter that's unfair, and there's just a wide variety of these things, and that's sort of what's in the middle. And what really you're trying to do as an attacker is synthesize a transmitter on the one side, which is running inside of the victim protection domain, which allows, obviously, privileged access or whatever access that you have for your own code if you're the victim, and take the information from the victim code, victim data, and propagate it through the channel to a receiver on the attacker side, right? And so an old 20-year-old side channel that is something that says conditional execution in cryptographic algorithms such as RSA, where you do different things based on the secret bit corresponding to a private key, where you bring things into the cache, or your completion time, or just the work that you do is different in the if branch versus the else branch, and that's going to be a channel. right? So that's an example. But more sophisticated examples are things like meltdown, which correspond to a bug in the processor pipeline, and even more sophisticated examples, which give you a really rich attack surface if you're an attacker, are things like Spectre and Meltdown, where they're actually synthesizing transmitters from victim code, sort of putting together pieces of code that exist in the victim and have the privilege of the victim, and using that to exfiltrate information through particular side channels. And usually, most of the attacks that are out there and the ones that have gotten a lot of press are using the cached timing side channel, because it's a kind of a relatively low noise, high bandwidth side channel. But this picture really is evocative of a whole class of techniques. And as I mentioned, really the side channels are everywhere, right? It's if you look at a computer system and there's tens of millions of lines of code corresponding to the operating system, there's complexity associated with the hardware. This hardware is only getting more complicated. The hardware designers want to know how to use, for better performance or lower in energy, all the real estate that they have. And so there's a lot of sharing associated with these hardware constructs, because you don't necessarily just want to do accelerators. And there's side channels everywhere. There's bandwidth side channels, there's storage side channels, there's completion time side channels, and it's only getting more complicated. There's also more domains, of course, right? I mean, you have many victims, you have time sharing, and you have the operating system, you have hypervisors, and so there's different privilege levels as well. So this is a fairly complicated situation here. So our philosophy really has been, for really more than a decade, is build enclaves, not just processes. Enclaves have an associated threat model, and you can obviously vary that threat model. You need to do more work, obviously, for the more aggressive threats, and build an enclave platform. So change the computer architecture, do hardware software co-design. So you build an enclave platform that doesn't just support processes, but supports stronger notions of processes, namely enclaves. And obviously, I'll say a lot more about this as I go along. And so enclaves need to strengthen the process abstraction. And the idea is that if you have a threat model that includes side channels, then enclaves should be resistant to those side channel attacks and what have you. You want to guarantee isolation of memory. That's really what it comes down to. The memory that the victim owns, should be just readable by you, writable by you, and there shouldn't be other ways of extracting that information. And essentially, what we have here, as you see in this slide, is you want to have this privacy guarantee, and I'll let you read that. That's associated not just with the architectural state, which really computers are giving you. Architectural state is not readable by attackers. It's really the other state that is supporting the architectural state that is causing problems. And the other thing that enclaves can do for you is decouple performance from security considerations. So the idea is that you pay for protection. And so you have these stronger processes that you pay more when you enter them and when you exit them. And you don't pay, ideally, you don't pay at all for unprotected processes, which is essentially running on public data, and you don't particularly care about privacy for those processes. Hardware is a complicated thing to build, and it also takes a long time to fabricate chips and deploy them. And so generally speaking, you don't want to make dramatic changes. I mean, if you want to go make dramatic changes in the AMD or the Intel or the ARM processor pipeline, that's going to take you a decade. But if you change the interfaces of hardware components, it's less invasive, and you may have a chance on getting into the next product. Now, of course, we do clean slate design in academia, but we do keep this in mind in terms of the amount of hardware change that you want to make to your conventional processor. It also makes sense that if you make more dramatic changes, that you have to reason about those more dramatic changes from a standpoint of security, and it might also affect the performance, right? And then lastly, you'd like to have some sort of argument, whether it's a cryptographic argument or in most of the cases here that I'll describe, it's an invariant. You'd like to have provable security, and this may be manual, this may be formal. I'll say a little bit about that as I go along. And there are some downsides to enclaves and building enclaves, and I'll say a little bit about that at the end of the talk. But this is motivational. And so the other thing I want to talk about before I dive into details is who do you trust? Right? So you have a trusted computing basis, and it's 100 million lines of code, maybe more when you're trusting Amazon Cloud, and it's the entirety of the computer system. You trust memory, etc. And so there's been this effort that corresponds to secure enclaves under untrusted operating systems that really tries to shrink the TCB, right? And there's also obviously coprocessor work like TPMs and so on and so forth. So you'd like to shrink the trusted computing base, and this slide is 16 years old, and I guess the chip in the middle there looks like it's from the 1950s, but it's just clip art from 15 years ago, and you can see the CRTs and so on in the slide. But this is, again, a slide that essentially says, here's what the ideal world would look like if you tried to minimize your trusted computing base and you tried to essentially build enclaves in this type of architecture. So you just trust the computer chip in terms of the hardware. It has an attestation capability because you can't see inside of it, so it's going to have to do some measurement, and then it's going to have to verify that the software that you're running is in fact the software that you expect to run. So that's why you have a secret key in there. And you can build this in many different ways, but the way we build this is we don't trust the operating system, and there's a kind of a baby operating system or security monitor, that's what we call it, that corresponds to maybe about 5,000 lines of code in our implementation that is trusted, and it doesn't do the work that the operating system does in terms of resource allocation, the decisions, the intelligence associated with that, but it checks invariance. It checks invariance associated with isolation of memory, right? So that's why it can be simple. And you have to protect side channels that correspond to memory, and also there's obviously side channels inside of it. And I will say that when we made this slide 16 years ago, we didn't think side channels were going to be that big a deal. But certainly the notion of shrinking the trusted computing base is something that this slide describes, and you'd like to take that 10 million lines of code and shrink it down to something much less that is potentially formally verifiable. So let me tell you a little bit about enclaves and what we're trying to build here. And so essentially you think about some enclaves as being containers, and you are very careful about what these containers contain, and you measure them. You measure them cryptographically, and the operating system creates them, and puts a program and code inside of them, and there's no sensitive code inside. It's all public at that point, and it does a measurement, and then only after that measurement will sensitive code or sensitive data be sent in an encrypted way to reside inside of the enclave. So that's one part of it, and the other part of it is that you obviously running inside of the enclave, and sometimes you have to go out and make system calls and come back in. And you have to be super careful about essentially the state that's associated, obviously not just the architectural state, but also the microarchitectural state associated with supporting this enclave, and make sure that you clean up after yourself. And Daniel and Yuval gave a great talk yesterday about issues that come up with not cleaning this microarchitectural state, and how you have attacks based on those those errors, if you will, with respect to not flushing things and leaving things behind you, right? So you have to do that. But that's essentially what we're trying to support here. And the isolation goal is, roughly speaking, and I'll let you read the details over here, is you want to have a high-level property that essentially says, you know what, even though you're on the machine and you have privilege as an operating system, you can't do anything worse than what you would be able to do if you were away on a completely different machine, right? So this is essentially something that top level you want this goal. You got to break this down into a bunch of invariants if you want to actually go off and prove things about it, and you have to say things very explicitly about state and so on and so forth, each piece of state. What I want to point out here is that we're assuming well-written programs. I mean, if a program is dumb enough for it to write out its secret, its private key over on standard out, I mean, this doesn't protect that, right? And so we're not protecting against programs that leak secrets through their API. It's really outside of the API attacks that we're trying to protect against. There's basically three strategies for isolation. There's spatial isolation, temporal isolation, and cryptography, right? I'm not going to say a lot about cryptography, so sorry, real-world crypto, but it's mostly about isolation, spatial isolation, and temporal isolation corresponding to these architectures. Cryptography does have some role here. I'll briefly mention that. So I want to tell you about a couple of processors we've built. One of them that was built a couple of years ago, and a processor that we're in the middle of building. And so this was designed by Victor Kostan and Ilya Lebedev, a couple of my PhD students. So it's based on the RISC-V, and so you also had a talk on the RISC-V yesterday. And so RISC-V has this particular, and Sanctum has this particular software stack. And essentially what you see here is what you trust is the hardware, and what you trust is the enclave, which is really the code that corresponds to the victim code, if you will. You need to trust yourself. And then on the top side, RISC-V has a machine mode, and this is where the security monitor, the trusted part of the operating system, runs. And so this is the equivalent of microcode in SGX, for those of you who are familiar with it, except that this code is relatively small and also written in high-level C. It's written in C99. It's about 5,000 lines of code in our implementation. So you can actually look at it, and you can vet it, you can audit it. These things in the middle are untrusted, and we don't need to say much about it. I'll just say that the measurement root is essentially something that corresponds to cryptographic attestation. You have a situation where you also have this, obviously, the security monitor that I've mentioned before, and together the trusted computing base corresponding to what's on the top, and obviously the enclave code give you your enclaves and your security guarantees. And all of this is based on a particular threat model that you've chosen. And so this particular processor we built, did not have hyperthreading in it. It's a RISC-V Rocket, no speculation. So the number of microarchitectural side channels was much less. If you look at the isolation that we have to do here in Sanctum, for things like private TLBs and register files, they're private to you, so you have to flush them. And so that's your temporal isolation. But then you do have shared caches and shared TLBs that you want to maintain state as you come in and out of these enclaves, because otherwise the performance would just go haywire if you keep cleaning up all of the intermediate computations you've done. And for that, you need spatial isolation. And so I want to talk a little bit about some of the interesting things in Sanctum that have in this particular case, fixed problems in SGX. And so the API, I should say, for Sanctum, it was certainly motivated by SGX and the terminology as well. And so if you look at the operating system being untrusted, it is doing a lot of management for you. It's managing the page tables. And there's side channel attacks associated with these page tables and knowing what pages are being accessed. You can imagine that that would be a break, right? And in SGX, I would call this a design flaw. The operating system is capable of, the malicious hypervisor is capable of looking at page fault addresses and also modifying the page tables to increase the number of page faults that happen. So essentially, you're in a situation where one of the older attacks carried out by Microsoft on SGX was something that said, well, if I'm trying to protect this Rubik's Cube and this is my secret data that's associated with the enclave, and I'm trying to compare this with a whole bunch of other public databases, and all of this is going to happen inside of an enclave, then this page fault bug, a design flaw, was essentially something that allowed the attackers to discover what you see down at the bottom, which is every once in a while you see a pixel or the value of a pixel associated with this particular cube, which is really a coarse rendition of this cube. And it comes because you're not seeing every memory address, but you're seeing every memory address at the page level when you move from one page to another page. So you have to be careful here when you have an untrusted operating system associated with what you give it, what privilege you give it, and if you have to ensure that that privilege that it has doesn't allow you to do these kinds of things. And so in Sanctum, we've changed the page table management to be something where you had two sets of page tables associated with the enclave page tables that corresponded to enclave memory that belonged to the enclave, and then the page tables corresponding to shared memory that were controlled by the operating system. And this required a hardware change. I'm not going to be able to describe to you the specifics of the hardware change, but you can think of it as dual mode page tables and some multiplexers in the logic that allow you to decide which way to go. And then the one other example I'll mention corresponding to protecting against cache timing attacks in Sanctum was simply to take the shared cache and break up the shared cache into partitions that are, this is spatial partitioning, and so you have a situation where the enclave and the OS are completely isolated in the memory hierarchy, where you don't have a situation where they're sharing cache sets or cache ways or what have you. There's a couple of different ways you could do partitioning, and we chose set partitioning in Sanctum. And so what does this mean exactly? Well, you could use page coloring that perhaps many of you are familiar with, and the page coloring is based on the fact that there's an intersection between the cache set index bits and the physical page number that corresponds to this DRAM region. These DRAM regions are essentially going to be regions in memory that are going to be isolated in the shared cache as well. And so pictorially speaking, you might have something like that where you see on the right, where you say you have the shared cache on the right, and you've colored these things just like you did with page colors, and each of these different processes has different colors and different cache sets. And then what happens if you just do this in kind of a naive way is that you now break up the DRAM into different regions as well, corresponding to the different colors. And this is a little bit annoying from a performance standpoint, because you have a situation where these colors are spread apart. And so then again, a little bit of bit shifting in the hardware, and so that would be a change in the hardware, is going to give you the picture that you see here, where you have contiguous DRAM regions, as well as obviously you have the contiguous shared cache regions. Those are all sets anyway. And so these are the kinds of performance tricks that you have to play in order to sort of get back the performance when you had to do isolation in a stronger way over and beyond conventional processors. So a few other changes in Sanctum. Just to give you a sense of the kind of invasive changes that are made in Sanctum, this is a Rocket Core chip, and the colors that you see are the modifications that were made in Sanctum. And so most of the colors that you see are flushing state, so you have these storage of state and you're essentially clobbering the state. And then you see a little bit of blue in the middle there. Those correspond to these dual mode page tables. And so the whole thing was about 2% different in terms of area. So you can see that this is not a dramatic change to go from a process abstraction to an enclave abstraction. All right, so this is really what we did a couple of years ago. I want to briefly mention some work that I did with collaborators. And I'm not a formal verification expert, but I did stay in a Holiday Inn Express last night, or more seriously, I stayed here last night, and I'm not any smarter, but I work with people like Sanjit Seshia and more recently Adam Chapala on thinking about formally verifying these properties of enclaves. So really briefly, only because we're in a formal verification session, I noticed the title a few days ago. And so I want to talk to you a little bit about the adversary, that we can formally model the adversary. We can formally model the threat model based on observation functions and tamper functions. And you have notions of enclaves. And really the thing I want you to take away from this is that there's three aspects to enclaves that need to be put together to get essentially this sort of secure remote execution or secure execution capability. The isolation goal, which is measurement, integrity, and confidentiality, and there's invariance associated with each of these things. And the work that my group did with Sanjit was essentially using model checking and SMT solvers to take an abstract specification of Sanctum that included both the security monitor as well as the hardware. And essentially there's this thing called the Trusted Abstract Platform, or the TAP, and we wrote invariants for these things, and essentially verified these invariants using this SMT solver. And there were a few things, there's certainly a few bugs that were discovered in our specification that corresponded to violating these invariants, and we went and fixed them. And so I mentioned the threat model, and it's important to keep that in mind, because if you look at the observation function and the tamper function, that's obviously an important consideration in whether you have security or not, perhaps the most important consideration. And SGX is in fact secure under a fairly limited observation function where you ignore side channels and you ignore, essentially shared caches and so on and so forth. And Sanctum sort of raises the bar a little bit, at least from a standpoint of the threat model. And so you can show a refinement proof that essentially says that under this particular threat model, corresponding to shared caches and some limited number of side channel attacks, that you won't have breaks in Sanctum. I mentioned that it does not include speculative access. So if you had ways of speculatively executing code, then the threat model would have to be different, and we wouldn't be able to do that proof for Sanctum, right? So we built Sanctum. It's running on essentially it's a RISC-V processor running on an Amazon FPGA. And as I mentioned, there's an ongoing formal verification effort. But I want to say that this is an academic and a lightweight processor. It's a microcontroller scale processor. And one of the things that is something that we started thinking about was, especially after Spectre and Meltdown came out, so 2018 was really the year of Spectre and Meltdown and processors getting broken, thanks to Daniel and Yuval and their collaborators, is what would happen? What would happen to all of the things that I've told you when you look at bigger processors, more heavyweight processors, including things that have speculation in them. And so we did some work on that, and from the few minutes that I have left, I'd like to describe that work. This is done by my group and Professor Arvind's students, who's a close colleague of mine. And Thomas is here in the audience, and so you can talk to him as well. And you can see, we have a cool name for it, or at least I think it's cool, corresponding to this particular processor. And the reason for that is we're going to make an argument that this processor defends against Spectre and Meltdown type attacks. And the question is, we take what I've told you right now, what changes when you go to a much more sophisticated processor, right? And it is, in fact, much more sophisticated, okay? So now I'm calling Sanctum a toy processor, not just an academic processor. I didn't say that a year ago. But if you look at the complexity of superscalar, out-of-order execution, it's way more complicated than in-order processing, namely the rocket chip, and that's what Sanctum is based on. So think about your computer architecture class, your graduate class, if you've taken it, and sort of the second half of the class, and all of the techniques that were in that class of speculation and scoreboarding and so on, and they're all in here in this processor that Professor Arvind and his students built, which is called the RISC-V processor. It, again, is a processor that we used as a baseline, but it boots Linux and runs on an Amazon FPGA. And the key point I want to make here is that this processor is way more performant, right? So if you don't speculate in this processor, it's 3x less performant, right? And as much as 5x less on really a wide variety of benchmarks. So just turning off speculation isn't viable from a performance standpoint in order to essentially say that you have security, all right? So that's really what I want to show here. It's complicated. The processor is complicated. There are a heck of a lot more side channels. We are discovering side channels that really haven't been published in this processor because we have things like non-blocking caches, and you don't just have a shared cache, you have many hardware modules before the cache corresponding to a crossbar. There's an arbitration mechanism associated with this crossbar, and if that arbitration mechanism is unfair, then there's a side channel associated with it, right? So the students here, Thomas and others, have sort of walked through the entire state. The wonderful thing about this is that we have the hardware right in front of us. It's open source. We can look at the hardware. It was written by a grad student. We can look at every state in the processor and figure out if there's a side channel here or not. Right. So, and in fact, like I said, we've discovered some side channels corresponding to the unfairness. It's not just cache side channels. And so really quickly, you can do the same philosophy that I've talked about here, which is you can flush microarchitectural state every time you go inside of the enclave and come out of the enclave. And if you do that and you run benchmarks to completion, every time you do a system call, you have to essentially do this flushing of the state. The performance overhead is 5%. So this is an overhead associated with the enclave, right? Because you're going inside and outside of it. If you didn't care about security, you wouldn't have this overhead. The last level cache is a problem. It's a serious side channel. We have to do spatial isolation for that. This, unfortunately, is something that affects protected programs as well as unprotected programs because you have to share this cache in this more constrained way, right? So there's an overhead associated with that, and you could imagine you could try and shrink that with smarter partitioning schemes. We're going to look into that when we have time. Every time you're going to copy state from outside of the enclave to inside of the enclave, even though it's obviously public state, because it comes from outside of the enclave, you have to be super careful, and the conservative way of doing this is to turn off speculation, right? Now, if you turned off speculation overall, I mean, that's untenable like I described, but only the times that you're copying state, if you turn off speculation, then the overhead is essentially negligible, because you're only doing that it's a very small fraction of the time. But you have to have all of these hardware modifications that I talked about with respect to the flushing, with respect to turning off speculation, the dual mode page tables. All of these things have to be built into the processor, and that part was done, right? So this is what I said about the negligible. And so overall, it's similar to the picture that I showed you. I don't have a picture like that, but it's about 2% difference in terms of essentially what you have to have. You have to have multiplexers, you have to have reset signals, and you have to make a bunch of changes in the hardware. And so this has been done. I should say that we don't have user mode enclaves running on MI6. You know, the software is essentially the Sanctum software. We've changed the hardware, but there's a lot of work to be done in order to actually get this to the point where we can hand it off to a Daniel or a Yuval and ask them to break it. But that's our intent. What's left? Well, a lot of things left, including implementation, as I said. One of the things that is associated with enclaves that's a downside, especially as the threat models evolve, is the fact that enclaves trade expressivity for security. Right? So we can't arbitrarily just make system calls. They have to be proxied. There's a collaboration protocol involved. Anytime you have adaptivity, you have dynamic memory allocation, you're interacting with the outside, you have to be super careful. Right? So there's issues associated with that. And in general, I think crypto could be useful in the context of adaptivity and provable security, when I'm talking about microarchitectural optimizations and doing things adaptively in hardware to get performance or to get energy. And one example is demand paging. So if you want to do demand paging securely, taking into account all of these side channel attacks, you'd essentially need, in my mind, the only way I know how to do this is page level ORAM and integrity verification and encryption in order to get essentially provable security when you want to do secure demand paging. Right? So there's other examples, but I want to leave you with that. And so let me just stop thanking all the people who contributed to this talk and this work, and thank you for your attention. So.
That's great. Thank you very much. Any quick questions, since we're running slightly behind schedule? So please make your questions short at this point.
I had one quick question on the speculation and turning it off and turning it on in order to do those copying operations. Question was, did you notice any performance degradation as a result of this in place now?
So we actually haven't done that experiment to the point where I can give you a number. Pretty much I left it at a qualitative level where, I mean, if you turn that off and for the whole time, it's horrible, as I mentioned to you. The copy operation, it's a function of the ratio of the times that you're turning this off. So you can think of it as 3x overhead for 1% of the time, or 0.1% of the time. And it depends on system calls. It depends on how many times you're doing this. In a batch style computation, you do the copy once. So in that sense, it's negligible. Okay.
Thank
in
you,
interactive
sir.
computation, it's more often. Right. So.
Okay. Thank you very much for that talk.
Thanks.
Wonderful. A quick announcement before you all go to coffee. We will be sending out a link for a survey. We'd like to get your feedback on RWC 2019. We'll be doing that sometime after lunch today, and we would really value your input and ideas for improvement of the conference. So look out for that. Thank you. Oh yeah, and give us money, Nigel says. Give us money.